Good afternoon, everyone. I'll be talking about eBGP Flowspec peering for DDoS mitigation. Sorry. Taking a quick look at the DDoS market scenario, the attacks continue to grow in terms of size, frequency, and complexity. Traditional mitigation techniques have involved use of scrubbers, which is basically taking an onload of good and bad traffic, scrubbing the bad traffic, and then offloading the good traffic back to the network. Most organizations used a scrubbing solution of 10 gig or 40 gig or maybe even less. However, various recent attacks have been more than 1 terabits in size, making it very difficult to have the scrubbing capacity to deal with them because 1 terabits is like 20 times the size of the best available scrubber. What this leads to is no other option other than just using remote triggered black hole. And RTBH is really not mitigating the attack. It is more of just protecting your network because you're just black holing all the traffic. Additionally, black holing commercial customers is not really a big option due to service level agreements. And besides, you have to deal with complaints from both residential and commercial customers. Some important statistics so far. While the number of DDoS attacks continues to rise in number, 75% of the attacks are still volumetric. They are simple, just volumetric attacks which simply occupy the channels, the pipes, and fill up so that you have service unavailability. Also, importantly, 60% of the attacks are less than an hour or under 6 hours. So most of the attacks are very short timed and they don't last for hours and hours or days or something like that. Since I mentioned it's most of them are simple attacks, they include DNS, NTP, LDAP or SSDP. For example, someone has an open DNS resolver and it is being used to spoof the victim IP and then send an amplified DNS answer. Also, NTP mon lists. The best practice is to block mon lists, but there are a lot of open NTP servers which do not do that. So what happens is scrubbers get busy mitigating these small attacks, and this is not really the best use of intelligent device like scrubbers. And when there is a major attack, a simultaneous large attack, the scrubbing solution is left with no capacity to deal with them. A quick look at the existing solution in practice in most of the service provider networks. We talked about scrubbers. You can either have several scrubbers at somewhere closer to your peering point, so it's more like a distributed solution, or you could have it a bigger scrubbing solution in your data center, so it acts like a centralized architecture. It's also best common practices, BCP38, to minimize the spoof traffic by enabling reverse path forward, RPF check on your routers so that there is limited spoof traffic. And it is also advisable to not let the DDoS traffic clink up all your channels, so it's best to block it as close to the source as possible. In recent times, Flowspec has been talked about a lot. The only problem is that Flowspec cannot be used on smaller routers because older hardware doesn't really support it. So maybe you're able to use it at your peering edge, but at most other like customer edge or something, you might not be able to use it so much. There is also DOTS, which is DDoS Open Thread Signaling. It has picked up in the last few years, and it is still a work in progress. So it will still be a considerable time before the architecture is ready for us to use. So here the solution that we are proposing and pushing for is DDoS peering, which is essentially eBGP peering with trusted service providers to exchange Flowspec rules. This is not a new concept. Some industry leaders from AT&T and CenturyLink in the past, NANOG 71, had presented the concept and explained it in detail. What we have done is we've done the implementation and a validation of the concept and see how it is working. I just wanted to clarify that this is not meant to act as a standalone solution for DDoS mitigation. nor it is meant to replace your existing solutions. This is for an enhanced DDoS mitigation. The simple and smaller attacks will be managed by this solution, while the complex attacks will still require use of your existing scrubbing solutions. So in this collaboration, we are having inter-ISP Flowspec. So one DDoS peer will send Flowspec advertisements to another peer, asking the peer to rate limit or block traffic to a particular destination IP address. The important criteria here being that there must be a destination IP address which is managed by the initiating peer. For example, Charter cannot ask a peer to rate limit traffic for an IP space which is not managed by it. In return, the DDoS peer will ideally use that rule, apply it across its network on the peering edge, and then filter traffic based on the rule. This is a high-level overview of how the solution works. Let's say we have 3 ISPs, ISP A, ISP B, ISP C. We have a victim in ISP A on which a DDoS attack is happening, and the victim is unable to access a valid website on the right side. ISP A and ISP B are participating DDoS peers. So when the attack is happening, the peering routers are sending the net flow information to a standard DDoS detection tool. It sends the net flow information about the number of packets and all the general regular stuff. The detection tool will run its algorithms to identify the type of DDoS attack, the port numbers, the protocol used, the packet size, and all of the details. This information is sent to the Flowspec controller. The Flowspec controller is present on both sides of the peer, ISP A and ISP B, and this is the central brain of the whole project. The Flowspec controller will get syslog messages from the DDoS detection tool, and it will construct a Flowspec advertisement and send the rule not only to its own peering router, but it will also send it across to ISP-B's Flowspec controller. The ISP-B's Flowspec controller will, in return, accept the advertisement, do some processing over it, run some validation checks, and then advertise it to its peering edge. Thereby, a part of the DDoS traffic is blocked even before it comes to ISP A. It's directly blocked either at source or while still in transit. Talking about the details of the proof of concept, we've developed the architecture layout and the implementation to receive Flowspec rules, do some processing, and then re-advertise them into the network. Since it's an eBGP relationship, obviously you cannot directly trust the rule sent by an eBGP peer. So we do not directly trust any route sent by the Flowspec peer. There are certain rules which the Flowspec advertisements must obey. The first thing is that all non-Flowspec rules are advertised. This is not for general BGP routing, so any general BGP routes will be completely neglected. Additionally, there should be a destination IP address present in the Flowspec rule. I'm assuming most of the audience knows here about Flowspec, so I'm not going into the details of what is Flowspec. But having a destination IP address in the Flowspec rule, it ensures that traffic is being blocked to a particular IP address and not just a traffic which is simply matching a particular port pair or a particular source IP address. Additionally, we only want to rate limit or block traffic for a single IP address. So in terms of IPv4, the IP address should be a /32, or in terms of IPv6, it should be a /128. Additionally, in network and security, logging is everything. So we are logging every information which we get from the peer. So any valid request, invalid request, BGP updates, validation checks, whether the rule was applied to the network, everything has to be logged so that it's easier for audit trail. This is how it does, how the processing is done for the rules which it receives from the peer. The mechanism for sending the rules from using the existing DDoS detection tool, the mechanism to automate that is still in process, but it is essentially the script will get that syslog from the DDoS tool, construct a Flowspec rule, and advertise it to the peer. So this is how it should work when in sync. there is an inbound DDoS attack on ISP1. The attack is detected by the standard tool, and it sends a syslog to the Flowspec controller. The Flowspec controller, in return, will send the rule, advertise the Flowspec rule to ISP second's Flowspec controller, which will receive the rule, run some validation checks, and then apply it across its peering edge. This way, the bad traffic is rate limited or blocked more closer to the source. This not only ensures a congest-free link and more cleaner traffic, but it also ensures that the peering router is not bombarded with just high traffic, which it cannot deal with. This is a workflow of how the script on the Flowspec controller works. The Flowspec controller is essentially using eBGP, which is an open source implementation of BGP. And it's a standard Linux server which has a bunch of Python scripts running on them. So when a rule is advertised by ISP1 to ISP2, this is the workflow which takes place on the server. The eBGP server is listening for Flowspec rules. It converts those Flowspec rules into JSON and sends it to the Python script. The Python script will log everything to a database for audit trail and then perform a series of validation checks. The validation checks are, it should have a destination IP address. The destination IP address should be a /32, and the IP address should match the ASN from which it is coming, so that this ensures that no ISP is hijacking routes or controlling the actions on routes for which it does not own. If there is any error in validation or something goes wrong, it will definitely raise an alarm so that later the initiating peer can be notified saying, hey, your rule was wrong, or maybe there was this problem in the rule. Once it does the validation checks and it passes, it is sent to a web UI. So on the web UI, the operator can see a list of all the validated rules, and it is shown as a pending rule. Once it is a pending rule, the operator can decide whether they want to advertise it in the network or they want to completely ignore it. Once the NOC decides to advertise it, it's simply a button. You click on the button, and it is advertised to the network, which is further advertised using route reflectors to the backbone or the peering edge. Once that rule is applied, all traffic for that destination IP address in the second ISP will be blocked or rate limited depending on the rule. So this helps to block the traffic closer to the source, and it ensures that there is a less load on the ISP. This is how the rule is withdrawn. Once the rule is withdrawn after the DDoS attack is stopped, the syslog goes saying, hey, the attack is stopped. A Flowspec withdrawal is sent, and then eBGP again receives it, does some processing, runs validation checks, making sure this was already accepted advertisement in the past. It's not a crafted packet or something like that. And then the rule is withdrawn from the peering edge. And then the normal traffic flow continues. We have a quick demo for this as well. So I'm not sure how it works. You have to click or something. OK. So as we see, this is the backbone router, and we see there are no existing Flowspec routes on the backbone router. On the Flowspec controller, we start the eBGP session, and it creates an eBGP session with the peer, and we run our Flask server to use a web UI as well. This is the web UI showing that currently there are no existing routes which have been received from an external peer. And now an external peer is advertising a particular Flowspec rule. As seen on the web UI, the Flowspec rule is seen for a particular IP address 5.6.7.8, for a particular source number 666, and there is a button to either advertise, or if you want to ignore, you just let it be there. As shown, the route is advertised, and then on the backbone router, you can see that the rule has received 5678, so source port 666. There is an also option to withdraw the rule if required. We will not withdraw it here, but if someone wants to manually withdraw the rule, that can also be done. So when the external peer will stop the advertisement of the Flowspec rule, it should automatically go into the system and withdraw that rule from the network. We refresh the page and see the rule is gone. We also verify it on the backbone router. As seen, the rule is no longer there. This process of using a web UI, that can also be completely automated, but since it is in the initial stages, we want to allow the operator to have the control over what it wants to advertise in its network and what it wants to ignore. These are the next steps in the process. We've started working this with a few service providers, and we are starting with rate limiting because that is more safe rather than just blocking all the traffic. The mechanism to automate the sending of DDoS detection rules, that is yet to be done, but it should be done shortly. Another interesting feature which we want to add in this project is to accept Flowspec rules from peering ISPs customers so that a customer can advertise it to its parent ISP, and that ISP can relay that same Flowspec rule to another DDoS peer. To summarize this, this works when you already have a trusted relationship with a service provider. You already are doing an existing BGP peering. You have the trust built in, and then you can have a separate DDoS peering session as well. This will enable the ISP to have less strain on the resources. The scrubbers are still kept for mitigating the complex attacks, and simpler attacks can be done using Flowspec. One more thing which I want to mention, there is a concern with Flowspec that, hey, how many rules will the router be required to advertise? Because most of the routers do not support a whole bunch of Flowspec rules. At any given time on a particular ISP, there are not more than 20 or 40 DDoS attacks happening simultaneously. So there should not be more than 20 or 30 Flowspec rules on the router. It's a long way out. It's difficult to get all ISPs to do it, but it's one step at a time, and I'm definitely looking forward to any feedback or constructive criticism from the audience. A reference of the materials. If you guys have any questions, we can go ahead right now, or you can feel free to contact anyone from this slide as well. Thank you.
Hi there, Roland Evans, NetScout Arbor. I think I said it right. A comment and a question. So one comment I have is something that I don't think you really touched on in the presentation, is that when you're doing Flowspec peering, inter-organizationally like this, there's a relatively high amount of technical information that you have to exchange with your Flowspec partner about what router, what platform, what line card, so on and so forth. So this is a little bit more complex technically than establishing, your basic destination-based remote trigger black hole type of scenario. So I just want to put that out there. But I have a question for you, and it relates to your comment about being concerned about an explosion of Flowspec rules, which would potentially overflow a TCAM. Can you talk a little bit about the policy on the router and or the route server that you're wrapping around these the incoming advertisements to act as a self-protection mechanism to avoid a scaling problem?
When you see a scaling problem in the script, there is a validation check to ensure that at a particular time there should not be more than like 20 or 30 Flowspec active rules. So it ensures that there are not more rules like that. And as far as the policy goes, we have specific communities set on the router to ensure that, hey, the rule received from an eBGP server, it is essentially Flowspec, and it will go to these route reflector or the peering edge or something like that. I'm not sure if I correctly answered the question, but if there's something left, we can.
No, that's good. Also, wrapping policy on the router to act as a belt and suspenders to control how many Flowspec routes it's going to accept from the route server, for example.
From the route server?
Right, to your edge router.
So in the Flowspec controller, the script there ensures that at a particular, because it can check how many active rules are present on the router. So it will not activate any more rules than like 20 or 30. So that is basically taking care that there are not high amount of Flowspec rules advertised.
Okay, so your policy is on the controller. Okay, Thank you very much.
Okay.
Toma Gavrichenkov, Curator Labs. So thank you. That's a nice presentation. I too like hacking around eBGP. But my question is about DDoS open thread signaling. I mean, I get your point that it's work in progress. That's right. But you are handling IPv6 prefixes. You're using Flowspec. In terms of ITF process, flow specification rules for IPv6 are farther from release than all the DOTS documents, at least the first pile of those documents. So is there anything else that maybe prevents you from using DOTS except for, you know, the process, because that's not how it goes?
Mm-hmm. Well, yes, for IPv6, we don't have the RFC yet, but almost all vendors have their own implementation of how they are doing it. So it will definitely be a challenge to address the IPv6 issue. Right now, we're just looking to deal with the IPv4 first, and then deal with IPv6 as it comes.
Okay, thanks.
So I'm Jeff Haas, and I'm with Juniper Networks. I'm a big advocate for Flowspec, work on it inside of our BGP implementation, do work at IETF and the stuff. And I'm thrilled to see that you're recommending inter-domain Flowspec, and you should be terrified. There's been a number of really scary bugs in various implementations from more than one vendor, including us, over the years. You want to make sure that whoever's participating in this is running current code, and you do a really strong conformance suite to make sure the stuff is going to work. Otherwise, you'll end up with some unpleasant surprises. Mm-hmm. But that said, it's not a bad idea, but there's definitely some strong operational caveats here. I'm happy to talk about them offline.
No, I definitely agree with that. We've also discovered various bugs that, hey, this is supposed to act in this way, but it's not acting. So that will definitely be a challenge. So right now what we want to do is start in the lab and stick to what we've tested and only go with those rules. But I definitely agree with that.
Don Smith, CenturyLink. Don Smith, CenturyLink. And we discussed, Nimrod and I did actually, the idea of bringing customer routes, black hole filtering, Flowspec, et cetera, for the other peer. The fact is, depending on how they implement it, you might not even know it's a customer route. You may not know that it's really for the customer as opposed for protecting them. So you kind of have to just allow that one. That's pretty much a given. But one of the things I'm really interested in, I don't think I heard it, are you looking to do SNMP polling or something to check the health of the router routinely after you apply Flowspec rules?
Right now, we haven't touched that part yet, but I think that's a good feature you mentioned, and we should definitely add that in this as well.
Thank you.
Nimrod Levy, AT&T. First, I wanted to thank you for following up on our previous presentation and beating all of us to the punch and getting something actually implemented. So the first thing I had was about the validation suite that you have, and you said that you wanted to do validations so that the only routes you would accept from a peer were routes that had the same origin AS for the peer. That would prevent me, for example, I have a DDoS mitigation service, so I wouldn't be able to advertise a route to you on behalf of one of the customers that I'm working on a mitigation for. What I would recommend for that would be to, rather than checking the AS, would also be to look at, see if the route is, if you already have a next hop to me for that route. So if the best path, if you have a best path that comes to me, then that would be a valid route for you to accept in Flowspec.
I see, got it. Yeah, I think we'll definitely add it that way, and definitely we'll contact you, so making sure this is what we're doing.
Yes,
cool.
Thanks
Thank
again.
You. Yeah.
Me. Hi, over here.
Oh, sorry.
I'm hard to see. Can you talk a little bit more about the web UI that you're using to verify and implement the rules?
Yes, I mean, it's just a standard Flask server, using like GUnicorn or something. So it's not meant to be a UI for like a high use. It's just for the NOC or the SOC team to spin up the UI. It will display a list of rules which have been validated and are awaiting the operator's approval for advertisement. And then it will have a list of IPs which are already advertised, and then which you can withdraw them from the network as well. And then it contains details of the Flowspec rule.
Okay, thank you.
Sure.
This is Jugirta from Facebook. So during testing, what are the different factors that would play a role in taking the time between detecting and then going in the controller and pairing with the controller communication? So what's that timeline we are talking about here?
Right. So there is no significant delay for the controller to process it. It's only the delay is just the minimal delay which the standard DDoS detection tool will take to send that syslog to the controller. The controller will identify it and then construct a Flowspec rule for it. As far as the advertising that rule on the second peer, it's, yes, the operator, it'll take some time for the operator to look at the UI and decide whether they want to accept this or not. That can be completely automated as well. In fact, it is automated. We purposely kept it manual because in the initial stages of the project, we want to give the peer the control to decide whether they want to advertise this in their network or not. But apart from that, there shouldn't be any significant delay. Thank you. All right, thank you.